We've been working with the derivative for quite a while now, and we've been using the formal definition of the derivative. But now we're getting into these differentiation rules that we can use in order to take the derivative without having to use that formal definition. And so we started to get through some of these rules that are in front of you yesterday, and then we're going to continue to get through the rest of these rules today. There's even more, but we'll get through the rest of these rules today, and we'll continue proving why we can use these using the formal definition of the derivative. So far we have proved the constant rule. If you have a function f of x equals a constant, then the derivative of a constant function is equal to 0. We proved this constant multiple rule, which says if g of x is equal to c times f of x, and we said that f of x had to be differentiable, then g prime of x was equal to c times the derivative of f of x. We proved the power rule. We only did this for positive integers, and we talked about that we could not do this for all integers, that this rule does hold for all integers, exponents. If f of x is equal to x to the n, then to take the derivative, we're bringing down our exponent, n, times x, and then subtracting 1 from our exponent. We talked about the sum and difference rule, but we have not proved that. So we're going to start by proving that one today. We'll prove the product rule and the quotient rule, and then we'll get into a lot of examples of doing these. So let's look at the sum and difference rule. So the sum and difference rule says if, let's say, f of x and g of x are differentiable functions, and we have some function h of x, which is equal to either the sum or difference. So f of x plus or minus g of x. Then we can say that the derivative of our h of x is just equal to the derivative of our first function f of x plus or minus the derivative of our second function g of x. So let's prove this. Let's prove it for addition, but it also holds through for subtraction. So let's look at the proof of this. And so we're given h of x is equal to f of x plus g of x. In order to take this derivative, h prime of x, using the formal definition, recall this is a limit as h approaches 0 of f of x plus h, then plus this g of x plus h. That's just our h of x plus h function, minus the whole h of x, which in our case is f of x plus g of x, all over h. So let's just go through and rewrite things and break it up. So let's first distribute this negative to our h of x function, which is the quantity f of x plus g of x. So doing that, we have, this is the limit. I didn't want that color, sorry. The limit as h approaches 0 of f of x plus h. Notice here, and let's just rewrite it now as we're doing this. This is minus f of x. So let's just move that minus f of x right here. Doesn't matter the order that we write these groupings as long as we're carrying the sign properly. And then we have a plus g of x plus h. Excuse me. And so we just distributed this negative, and so this is minus g of x. This is all over h. So we can rewrite this. Basically, we could rewrite this as two separate groupings. I could, because this is a single term in the denominator, rewrite this as 4 separate fractions. But instead, I want to write it as 2 separate fractions and ones that look familiar to me. Right here, this f of x plus h minus f of x, if that is over h, that's just the definition of the derivative of f of x. And if I break it up where plus another fraction, g of x plus h minus g of x all over h, that again is the definition of the derivative of g of x. So let's go through here and rewrite this. So this is the limit as h is approaching 0 of f of x plus h minus f of x all over the grouping of h. And then we have this plus in between g of x plus h minus g of x all over h. But rules of limit says if we have something where the limit exists and we have a sum, we could break it up as the limit of the first piece. So limit as h goes to 0 of this first piece, f of x plus h minus f of x all over h, plus the limit as h goes to 0 of the second piece, g of x plus h minus g of x all over h. And again, this is just the definition of the limit or the derivative of f prime of x plus the derivative here of g prime of x. And this was our h prime of x. So h prime of x is equal to the derivative of the first function plus the derivative of the second function. And that is what we were trying to show. So we showed what we wanted to, we finished our proof, and we did that. So questions on that? So let's look at an example of using this rule. We're going to look at a couple of examples, and then we'll get into the product and the quotient rule. But right now, we can use multiple rules here. We can use our general power rule. Which says if y is equal to x raised to the nth power in a real number, then y prime is equal to n times x raised to the n minus 1 power. We can use the rule that the coefficient times a function. Oops. Constant k times a function f of x. So if our function f of x is differentiable and k is a constant, then when we take the derivative of this, y prime is equal to k times the derivative of f of x. And then we can use the sum and difference rule, which we just talked about. Okay, so let's go through this. So we're going to take the derivative, and we have f prime of x is equal to our constant in front, 3, all times the derivative of x to the 5th. So using this general power rule, we're bringing down our exponent 5, x, and then we're subtracting 1 from our exponent. 5 minus 1 is 4. Minus 6, all times the derivative of our x squared function. So using the general power rule, bringing down our exponent of 2, x, and subtracting 1 from our exponent gives us 1. Plus 4 times the derivative of x. Well, this is an exponent of 1. So if we bring down the 1, which we normally wouldn't write this, x, subtract 1 from our exponent, 1 minus 1 is 0. Plus pi, if you see just pi and there's no variable here, this is just a constant. Sometimes you might just see e there and it doesn't have the variable attached. E is just a constant. So the derivative, recall, of a constant was 0, so plus 0. So let's just go through, simplify this up, and then we're done. So we have 3 times 5 is 15, x to the 4th, minus 6 times 2, so 12x, plus 4 times 1 is 4. And recall, x raised to the 0 power, as long as x is not 0, is 1. Plus 0 is 0. So we found the derivative by using those rules, which is 15x to the 4th minus 12x plus 4. So that was a lot faster than having to go through and use the formal definition of derivatives. So some of these examples, when it's asking you to find the derivative, we haven't used or know those rules in order to do this. Right now, I have a product of 2 functions, and we haven't talked about taking the derivative of a product of 2 functions. And we'll find out soon that it's not equal to the derivative of the first times the derivative of the second function. So, but we do know is that we can expand this by distributing. And once we've expanded this by distributing, we can use the rules we know to find the derivative of y. So we have y is equal to the quantity 2x plus 3, all times the quantity 5x squared minus 4x. It asks us to find dy dx. That notation is just saying find the derivative of a y with respect to x. And so before we do this, we want to first rewrite this. And so let's distribute. We have a 2x times 5x squared. And so that gives us 2x times 5x squared is 10x cubed. Then we have this 2x times this negative 4x. Well, 2 times negative 4, so minus 8. X times x is x squared. And now let's distribute the 3. So 3 times x squared, that is going to give us plus 15x squared. And then 3 times negative 4x gives us minus 12x. Before I take the derivative, I would see if there's any like terms. I would combine them if there was, and there are 2 like terms. So let's rewrite this. So this is y is equal to 10x cubed negative 8x squared plus 15x squared, that's a plus 7x squared, minus 12x. So now it's in the form that we know how to take the derivative. We're going to use that general power rule, the constant times a function rule, and the sum and difference rule of derivatives. So coefficient in front 10 times the derivative of x cubed. So we're going to bring down the power 3. All times x, subtract 1 from our power, we get 3 minus 1 is 2. Plus, we have 7 times, take the derivative of x squared, so bring down our exponent 2, times x, subtract 1 from our exponent, so 2 minus 1 is 1. We really don't have to write that 1 there when it's an exponent of 1. And then we have minus 12. And the derivative of the x. Well, the derivative of the x, you'll find is always 1. So let's simplify. So dy dx is equal to 10 times 3, so that's 30x squared, plus 7 times 2, so that's 14x minus 12. Well, so let's look at that same example and let's say that, oh, it tells us that we want to find dy dx. And let's assume that we think that we can just take the derivative of that first quantity, 2x plus 3, and then multiply it by the derivative of that second quantity, 5x squared minus 4x. Let's see if we get the same exact result that we just did when we took the derivative by expanding and using the rules we know. So let's ask ourselves, is dy dx equal the derivative d dx of our first function, which was 2x plus 3, times our second function, actually let's do it this way, times the derivative of our second function, d dx, and the second function in this case was 4x squared. Sorry, it was 5x squared minus 4x. Okay. So let's try it. dy dx, is this equal to, so if we take the derivative of our first piece, so the derivative of 2x, well, the derivative, we'd have our 2 times the derivative of x, which is just 1, plus the derivative of our constant, 3, derivative of a constant is 0. Is this equal to 2 times 1 plus 0 times the quantity? So the derivative of 5x squared, well, we have our coefficient 5, derivative of x squared, that's 2 times x, subtract 1 from our exponent is 1, minus the derivative of 4x, which is just 4. So let's simplify. So first piece, we have 2 times 1, which is 2. Second piece, we have 5 times 2x, which is 10x, minus 4. Well, let's distribute. So if we distribute that 2, we get 2 times negative 10x, that's negative 20x. Sorry, 2 times 10x, which is 20x, and 2 times negative 4, which is minus 8. And this was our dy dx. Notice that these do not equal each other. So the derivative of our function, if we have a function times a function, is not equal to the derivative of the first function times the derivative of the second function. So that is actually a common mistake that students make, and they want to do that. But you need to learn this product rule. So let me just give you the product rule and we'll go through that proof. Okay, so the product rule for finding the derivative of two functions. So let's say you have two functions which are differentiable, maybe call them u and v. So if u and v are differentiable, at x, then their product u times v is the following. The product, maybe I didn't say that right. Then their product, the derivative of their product, let's say it that way. Then the derivative Can't write derivative. Of their product is the following. So we can write it like this. So d dx of u times v. So this is saying I haven't taken the derivative yet, but I'm going to take the derivative of u times v. This is equal to u times the derivative d dx of v plus v. They write it, and they write it differently. They write it here, dv dx. It doesn't matter. I have the same, that meant the same thing, plus du dx times v. Okay, so in words, the derivative of a product is equal to the first times the derivative of the second plus the derivative of the first times the second. Okay, so I might do this because I normally teach this where you take the derivative of the first function times the second function plus the first function times the derivative of the second function. So a lot of times when I teach this, I'm saying it this way, but let's just talk about why those are equivalent. So the derivative d dx of our function of u times v, I would say is derivative d u dx, derivative of the first, times our second function v, plus our first function u, times the derivative of the second function dv dx. Those are equivalent. We just have them swapped. And because of the commutative property, and the commutative property holds here, they're equivalent. So either way that you want to do it or remember it, they're equivalent. Okay, so let's prove this. Why can this be, actually, before we prove this, let's go back to that example and maybe show that we get the same thing. So our other example, we just did and showed it was not equal to the derivative of the first times the derivative of the second. We had, sorry, I should have looked at it closer, 2x plus 3. All times the quantity 5x squared minus 4x. So let's say this was y is equal to, and it tells us to find dy dx using the product rule. So let's name our first function. And our first function, let's call it u of x. So u of x is equal to 2x plus 3. Let's call our second function v of x. Let our v of x function be 5x squared minus 4x. So let's look at the derivative of the first. So we could write it du over dx. Another way to write that, right? Equivalent notation or equivalent meanings, but different notation is u prime of x. So this is equal to derivative of the first. Derivative of 2x is just 2. Derivative of a constant is 0. So now let's look at the derivative of the second piece. And the derivative of the second piece, which we could write it as v prime x, or consistent with what we used for the formula, dv dx is equal to, so derivative of 5x squared, well, that's 5 times our exponent. So 5 times 2 is 10. Subtract 1 from the exponent. From x squared, we get x, minus 4 times 1, which is 4, and derivative of x is 1. So again, the rule stated this is equal to I was going to do it my way. This is equal to, let's just do it, the derivative of the first times the derivative times the second plus the first u of x times the derivative of the second. So let's put it together. We already did this work up here. So the derivative of u of x, that was 2. So let's bring down 2 times the second function. Our second function here is this 5x squared minus 4x plus our first function. Our first function here is this 2x plus 3. Put parentheses around it, times the derivative of the second. So the derivative of our second function we found to be 10x minus 4. So let's clean it up by distributing, combining like terms, and then let's show that that's the same answer that we had gotten before when we first distributed it and then took the derivative. And so distributing this 2, we get 10x squared minus 8x plus, so foiling this out, 2x times 10x, that's 20x squared. 2x times negative 4, so that's minus 8x. 3 times 10x, so plus 30x. And 3 times negative 4, so minus 12. Combining like terms, 10x squared plus 20x squared is 30x squared. Negative 8x minus 8x, that's negative 16x, and a negative 16x plus a 30x. That's going to give me a positive 14x. And the only constant I have left is negative 12. And so let's go back up and show that's exactly what we had gotten before. So 30x squared plus 14x minus 12 minus 12. I don't know if you, hopefully you can see that. That's small when I've done that. Let me see if there's questions and then we'll move on.